Welcome, everyone. I'm Rick Wychick, the Director of NAEHS, and I'd like to welcome all of you to the 170th meeting of the National Advisory Environmental Health Sciences Council. So I'm obliged to read the Sunshine Act. So pursuant to the government in the Sunshine Act, all aspects of this meeting are open to the public except the review, discussion, and evaluation of grant applications and related information. So with that, welcome everyone, and let me turn things over to Dr. Belshaw. David?
Thanks, Rick. So as we always do with these, we'll get started with introductions. So we'll go around the council members in person first. So Trevor, if you'd like to introduce yourself.
Hi, my name is Trevor Penning. I'm from the University of Pennsylvania, where I direct our P30 Environmental Health Sciences Core Center. I'm also a professor of pharmacology.
Hello, Karen Vasquez. I am from the University of Texas at Austin, and I am the department chair and professor in pharmacology and toxicology.
Andrew Holian, University of Montana. I'm director of Center for Environmental Health Sciences.
I'm Gary Miller. I'm a professor of environmental health sciences at Columbia University.
Hi, I'm Maria Savasta-Kennedy, clinical professor of law at UNC School of Law, where I teach environmental justice.
Yate, good morning. I'm Jana Ingram. I'm from Northern Arizona University, where I'm a Regents Professor in chemistry.
Good morning. I'm Darrell Hood. I'm a professor at The Ohio State University in the Division of Environmental Health Sciences, and I'm a Dean's Fellow as well. Good morning.
Good morning. I'm Carrie Hornbuckle. I'm a professor of civil and environmental engineering at the University of Iowa and director of the Iowa Superfund Research Program.
Good morning. I'm Andrew Geller, senior science advisor at the Environmental Protection Agency, Office of Research and Development.
Morning, Yulia Caro, Associate Director for Science at the CDC, Division for Environmental Health Science and Practice.
Good morning, Gokhan Mutlu from University of Chicago. I'm professor of medicine and the chief of the section of pulmonary and critical care.
Good morning, I'm Tim Greenemeyer, professor of neurology at the University of Pittsburgh, where I direct the Pittsburgh Institute for Neurodegenerative Diseases.
And then we'll have our council members who are on the Zoom introduce themselves. Phil, I saw you there.
Good morning, everyone. I'm Phil Bourne. I'm the founding dean of the School of Data Science and a professor of biomedical engineering at the University of Virginia.
And I don't think Irva is on the Zoom. Irva, are you here? And Andrew Jorgensen, are you on the Zoom? Okay. It's a little early for him. Susie. I did see Susie.
Are you talking to me?
Yep.
Okay. It's Susie Fitzpatrick, ad hoc FDA member. I'm the senior advisor for toxicology and chair of FDA's Alternative Methods Work Group. And thank you for having me here today.
And Patricia?
Yeah, and my name is Patricia Nez Henderson. I'm with the Black Hills Center for American Indian Health, located in Rapid City, South Dakota. I'm actually calling in from Winslow. CDC is actually here where they're doing a reverse site visit. So I'll just be with you for this morning, and then I'll be back tomorrow. Thank you.
And I don't think I see Tom Leveist on the Zoom either. Tom, are you here? Okay. And then we'll introduce the members of senior leadership, starting with Jay.
Good morning, everyone. Jay Ingrid Mathis. I'm the executive officer.
Good morning. I'm Janet Hall. I'm the clinical director.
Good morning, Daryl Zeldin, scientific director.
Good morning, Trevor Archer, deputy director.
And then members of the DERT leadership.
Good morning. I'm Linda Bass. I'm here. Acting chief of the scientific review branch.
I am Sri Naradur, acting branch chief for exposure response and technology branch.
Good morning, Sharon Beard, Branch Chief, Worker Education and Training Branch.
Good morning, Michelle Heacock, Acting Chief of the Hazardous Research Substances Branch.
Jenny Greer, Chief of Grants Management.
Christy Drew, Chief of the Program Analysis Branch.
Cindy Lawler, Chief, Genes, Environment and Health Branch.
Thank you all. For interest of time, we'll not introduce the DERT staff that are in the room as well. So a little bit of housekeeping, reviewing some quick Zoom etiquette tips. This meeting is being webcast, and it's important for us to maintain microphones off when we're not talking. We will be sending audio out, so sometimes sidebar conversations will be picked up by a live mic. We would like to avoid that. A reminder to turn off your video and to mute during the break. For bandwidth issues, we encourage you to leave your VPN turned off. At times when council members need to be absent from the discussions for conflict of interest reasons, we will be putting you into a virtual waiting room if you're on the Zoom. If you're in person in the room, we'll ask you to go out and sit in the lobby, and we'll pull you back in when that issue has been addressed in the discussion. For those on Zoom, you do not need to leave the Zoom. We'll put you into a waiting room, and we'll also bring you back into the Zoom when that discussion is complete. Any members of the public who would like to express views regarding any of the items being discussed during open session may do so by sending an email to the council email address, which is listed on the council webpage, and that is national.advisory.council@niehs.nih.gov, and that will come to both Liz and myself, and we can address those concerns from the email. For council members, we will be conducting all voting electronically using the electronic council book, and Liz can work with you on getting that done. Next item on the agenda is to review confidentiality and conflict of interest procedures. And so I will read this to you. Policies and procedures for preventing conflict of interest and confidentiality of grant materials are contained in the conflict of interest forms, which have been emailed to you this morning by Liz McNair. And that states, this certifies that in the review of applications or projects conducted by the National Advisory Environmental Health Sciences Council on September 12th and 13th, 2023, I absented myself and I did not participate in the discussion of, nor vote on, any applications or projects in which I, or to my knowledge, my spouse, minor child, or close professional associates have a financial interest, nor on any applications or projects from an organization or institution where I am an employee, consultant, officer, director, or trustee, am negotiating for employment, or otherwise have a financial interest. In council actions in which we voted on a block of applications or projects without discussing any individual one, the en bloc actions, my vote did not apply to any applications from any institution fulfilling the criteria in the preceding paragraph. Members should sign the certification and email them to Liz, or you can, for those in person, you can leave them in your folder on the table, whichever is more appropriate. And then we have an action to take this morning, which is the consideration of the minutes from the June 2023 meeting. These minutes are available on the NAEHS homepage, and council members were asked to review these minutes before the meeting. They are also included in the electronic council book. Is there any discussion of the meetings, of the minutes for the previous meeting? If not, may I have a motion to approve the minutes? And a second? Thank you. Council members, please vote in the electronic council book. And while we are getting the vote, just a reminder of our future meeting dates. Those are also listed on the council webpage. Our next meeting will be a virtual meeting held February 12th and 13th of 2024. Okay, we have quorum. Thank you. Rick?
Okay. Microphone back on. Well, it is truly a pleasure to welcome Dr. Josh Denny here this morning. And he's going to tell us more about the All of Us program. But most of all, he's the Chief Executive Officer of the All of Us program. He was named to that position, I believe it was back in January of 2020 by Dr. Collins. So before joining, he's extremely well qualified to function as the CEO of All of Us, because before joining NIEH, Josh was a practicing physician and held several leadership positions at Vanderbilt. These included Professor of Biomedical Informatics and Medicine. He was the founding director of the Center for Precision Medicine and Vice President for Personalized Medicine. So at Vanderbilt, he led discovery and implementation projects in precision medicine, including clinical pharmacogenomics and Vanderbilt's DNA Biobank. So he was a pioneer. He's been a pioneer in the use of electronic health records for genomic studies, including the initial descriptions of phenome-wide association studies and phenotype risk scores. So he was elected a member of the National Academy of Medicine, the American Society for Clinical Investigation, and the American College of Medical Informatics. And most of all, he's very interested in working with us at NIEHS and the environmental health sciences community to better integrate environmental data into the All of Us program. He's very thoughtful, and he realizes that those phenotypes that they're studying as part of the All of Us, at least some of them may be attributable, or at least partly attributable to environmental exposures. So Josh, it's truly a pleasure to have you with us today, and I certainly look forward, and I think we all look forward to hearing more about the All of Us program. Josh, I'll turn it over to you. I can't see you, though. Hopefully, through the magic of Zoom, we can. There you are.
Can you hear me?
Great.
Okay. Wonderful. Well, Rick, David, Trevor, such a pleasure. I so appreciate the opportunity to speak with you today and join your council. And I'll just share that today I'm actually in South Dakota. Patricia, I'm I guess in your state. I am here for the Indian Health Service DSTAC meeting, and then we'll be meeting tomorrow with the Cheyenne River Sioux Tribe, and it's great to hear some of the energy there and come to you from South Dakota. So let me see if I can hear. I'm going to share my screen and get this going here, and hopefully we're in slideshow mode and this is clear for everyone.
Yep, we got it.
Wonderful, good. Well, and also I should say you have at least you have one council member here that does double duty. Gary Miller, it's great to see you. Gary is a member of our advisory panel, as well as your council, and obviously see some other council members know as well, and it's great to get a chance to talk with you. I just point that as evidence of our longstanding commitment of thinking about the environment as a important contributor to disease, and we're going to talk some more about that. We should also have plenty of time for questions. So without further ado, let's get started. So our mission, which is probably familiar to many of you, is to accelerate health research and medical breakthroughs, enabling individualized prevention, treatment, and care for all of us. And we think of this in these three circles here, components of that. And it really everything starts with partnerships with what we aim is at least 1 million participants who reflect the diversity of the United States. And then to make a difference in discoveries, we got to deliver this large, rich biomedical data set that our participants donate for the greater good, and make this accessible to broadly for research in a secure way that maintains transparency and trust, and then to catalyze an ecosystem of communities, researchers, and funders with the vision that all of us is viewed as an indispensable part of health research in the future. And as we think about that, this conversation is part of this. Our partnership with NIEHS, the global community of environmental researchers, is one of the reasons we're here to try to stimulate that thinking. We have a set of core values that we established in the beginning, and that starts with participation being open to all in the United States. We want participants, of course, to reflect the rich diversity of the United States from the outset, Participants are partners with us. We want to really share and return value to them. We want them to have access to their information. We want these data to be broadly usable. Security and privacy are of first importance. And we want to broadly be a change agent to catalyze positive change in research. And I think there are ways in which we're seeing that grow as this program started. The return of information, the partnership with our participants, what we call participants, not subjects. All those things are things that certainly have increased. We're not the only programs doing it, and we really don't want to ever be the only program doing it. We want to be part of a larger global community that's really raising these efforts. I think that's the only way we'll make significant change in how things are, especially as we see the world in a slightly different place as we come out of COVID. We now, after launching in May of 2018, we have enrolled over 700,000 participants have joined and signed the consent form. People participate in different ways, and that was especially true early on in the program. Not until sometime in COVID did we have the ability to collect biospecimens, for instance, across the country. And so now we can collect biospecimens from all 50 states, and we have participants also in many U.S. territories. Over 500,000 have contributed biospecimens now. We have a number that have donated electronic health records, and even in addition to that account, we've nearly 400,000 there. We have participants who are sharing their electronic health record data through patient portal linkages and things like that. So the number is even higher than that as we work to integrate these kinds of data from different sources. The states where we have more people enrolled correspond to states in which we have largely healthcare provider organizations. Could be an academic medical center, could be commercial, or generally nonprofit in that sense. And also the VA and FQHCs are partners as well. As I mentioned, diversity writ large has been a real key focus of ours from the beginning through all of our engagement partners that we fund that are both national and local and organizations of those, through our healthcare provider organizations and their outreach efforts as well. And so we're nearly, you can see about 50% non-Hispanic white, so 50% not that of a number of different race and ethnicities, and these are all self-defined. And I like to point out too, this is the high-level question that participants answered as a single question on their survey for race and ethnicity, and then participants can further define. For instance, more than 90% of those who mark Asian give us further definition about their race and ethnicity. And then underrepresentation in biomedical research is much broader, of course, than race and ethnicity. And overall, more than 8% of our population is underrepresented in biomedical research. And that's is all those different categories there: income, disability, sexual gender minorities, educational attainment, rural location. We want to have broad geography as well. And, I'll just point out too, is this longitudinal relationship with our participants. Disability is one that we did initially have on our surveys, and that we launched through and did an update survey to our existing participants, I think last year. So that's one of the things that's been an important add-in to the resource. We collect the same kinds of data essentially from our participants, regardless of how they come in. If they, download the app on their phone and sign up from South Dakota, where we, as far as I know, I don't think we have a healthcare provider organization here yet. For instance, they could go on the website, they can sign up. We can send them a saliva kit. Many areas of the country, we can also send them someplace, or even sometimes send someone to their home to collect blood. And people can share their electronic health records. There's sets of surveys. We release about one new survey a year. If you come in and donate biospecimens in an in-person location, we also do a brief set of physical measures, and then wearable data. You can share wearables that you have your own. We call it your Bring Your Own Device, or BYOD program. But we also have given out 30,000 Fitbits to people who are underrepresented in biomedical research. And those data are not, that's something we just did over the summer and a little bit last year. And so those data aren't in the resource yet, but those participants are contributing those data to be part of a future resource. And so just zeroing in as we think about the environment right now, the basics information, which is our first survey, does collect data on home and work locations. Those are actually exact addresses, and I'll talk a little bit about how we expose those kinds of address information later. And then we have a number of other places where we capture some kinds of information that's relevant here. The social determinants of health information survey gets these items here, and so these gives us some environmental pictures of different kinds of things that could be used to complement. And like I said, we release new surveys, and so one of the things we're talking about, we'll talk a little bit later, is what we might do with the environment in the future. Returning value to participants is key to our program. It's part of the engagement effort, and before we enrolled anybody, we did engagement studios with potential participants in 17 cities, and covered 4 different topics. And these studios gave us different information, including what would be of value. Most people, it's about creating a future of biomedical research that is inclusive for them and will represent their populations, and paying it forward to their children, their grandchildren, their communities. But in terms of value for them, generally people told us genetic information, especially health-related genetic information, would be some of the most valuable things we could get back. But we also give survey data. If you donate through the patient portal, your electronic health record data, you get some visualization and aggregation of those data if you share from multiple sites. And of course, we want to communicate scientific findings out. We do lay summaries of scientific publications, and they can also read about studies that are being done. Every person who starts a workspace, those workspaces are exposed. And we regularly will do feature stories on some of those that are shared with our participants. This talks about our genetic return strategy. We started with genetic ancestry and traits, largely because it's easier in some ways to get started. And we drive that off of arrays. And this just covers ancestry and some non-health related traits that you can see here. This was launched, I'm not going to remember the exact date actually, but this was launched during COVID. And then we return health-related information as well. And this was launched in December of 2022. In this case, we worked with the FDA. We have an investigational device exemption for these, and have worked through the 2 kinds of major information we shared back. Hereditary disease risk for 59 genes that are all intervenable, actionable, things like cancers, hereditary cardiomyopathies, arrhythmias. These all have something to do. These are all returned through a genetic counselor. Our data so far suggests that, in others, most people probably don't know that they have one of these conditions, and it's a couple percent, 2 to 3% of the population will have one of these variants. And then pharmacogenetics, or we call the medicine in your DNA report, and that's 7 genes that have a variety of genetic influences on different medications that we find that most people actually, regardless of genetic ancestry, would have a actionable variant if they're exposed to the medication. Now, of course, which gene you might have an actionable variant for has very strong differences across different genetic ancestries. But overall, more than 90% of people would have an actionable variant if they happen to take the medication. So this is what those 2 reports look like. These have been tested with our population. We have a post-survey. People seem to understand them well. And again, genetic counselors do all the initial returns for the hereditary disease risk reports, and then are available for the medicine in your DNA reports. They're also available if you just want to go talk about your genetic ancestry, or if you want to talk about it before deciding to get these results back. What does it mean? You can talk to our genetic counseling service. We have native English and Spanish speakers, and we can support 200 languages through translation lines. And you can see what all 3 of these look like. They're multi-pages for the BRCA, in this case, the hereditary disease risk and the medicine DNA report. And you can see that we returned about 60,000 of both of the health-related ones now, and about 134,000 people have viewed genetic ancestry and traits. And that's available, and really we're caught up on new people enrolling for genetic ancestry and traits. We're letting about 5,000 people a week know about their health-related genetic results, and then they can choose to take it or not. We don't force any of this return, and we find that certainly there's a significant number of people who don't want to know, and that's fine as well. It's their choice. Getting genetics and creating a resource is important, and we intentionally focused, as you know, on diversity. And this just highlights, as probably most of you know, that genetics has been a place that's been particularly egregious in terms of a lack of diversity. If you look at genome-wide association studies that have been done, so this doesn't necessarily represent cohorts, but this is people that are any genome-wide association study that's been done, more than 90% of them have utilized European ancestry populations. And so you can just see we're quite a bit more diverse. And even amongst those who self-identify as non-Hispanic white, about 2/3 of those are underrepresented in another way from the questionnaires we ask. And so we think this is an important add to the research data set. And so getting the hands into researchers looks something like this. We have these multiple tiers. We have a large aggregation process across, we're a very fragmented healthcare system. So we have lots of different places that upload electronic health record data. Those data get amalgamated, harmonized with the privacy methodology set forth. We, of course, have other interfaces for bringing in physical measures and obviously all the genome data and curation and harmonization and joint calling that happens. And then we released through the public data browser. Anyone can go to that. You can get aggregate counts, see what SNPs are there, see what their genetic ancestry breakdown would be, for instance, and get a sense whether there's enough patients that that have it in their EHR record heart failure, for instance, if you want to do an analysis of that. And then the individual analysis is through the researcher workbench, all in our cloud. Registered tier and controlled tier are different layers of privacy methodology and information that's there. And then we're also supporting these sorts of resources and our participants for ancillary studies. And the first ones of those involved, one of the first ones of those was looking at COVID serology early in the pandemic. We now have started one with 18 other institute centers and offices across the NIH called Nutrition for Precision Health. And now we're talking about other kinds of ancillary studies, which we'll get into in a little bit. This is a screenshot of the public data browser. Like I said, anyone can go here, get a sense of the survey questions, the HR data that we have, the genomic data in this process. And if you search for something like cancer, you can see that the data have been harmonized. There's synonymy across it. We pull together the ICD-9, ICD-10, SNOMED codes. They all get amalgamated through use of a common data model and to help facilitate some of this process. And in the researcher workbench, this is for access and the row-level data analysis you can do. There's all the analyses are done in the cloud. We support R and Python. We also have point-and-click based tools to let you do things like build a cohort and review individual records and the kind of data in them. And the way it works is we have a passport access for researchers. So a researcher authenticates essentially against an institution that vouches for them, often with a master agreement, and then they can get started. And a new researcher coming onto the resource, if their institution's already signed up, can usually get started in a couple hours after they even first hit the website, if they go through all the training and the modules to learn about the system. And it's currently open to academic, healthcare, and not-for-profit organizations with intentional expansion to international access planned for this year. The access has these 4 major steps. It starts with once you come in, identifying that you have an institutional agreement, creating an account, there's mandatory training, which basic human subjects and specifics around our resource. We talk about potentially stigmatizing research and how research is made available. And as you create your workspace descriptions, that those will be posted publicly. There's some guidance on that and what that looks like. And then we have a resource access board that can also review things in the process, and especially anything that appears like it might be stigmatizing. Then you sign your data use code of conduct, and that gets re-signed annually. And in the process, I just wanted to show you one example. NAEHS is one of the institutes on here. You can see, and you can look if your institution is represented through the website, and whether it's signed up or registered, controlled tier, and the process of getting on. So what's the data look like? So this is our currently released data set. You can see it represents over 400,000 people. Survey responses being the most numerous of the types of data that a given participant would have, but even 15,000 Fitbit records linked to health data, linked to genomics. It's a smaller number for us, but it actually has quite a few data points, and you can see on the right the longitudinality of these kinds of things. So if you look at the longitudinality, you see that even the Fitbit data goes back to 2010, but a lot of the HR data from some of these sites goes back to 1980s. So you have the ability to do in silico longitudinal studies in this resource, even though we launched with our first pilot participants in 2017. Our genomic data set includes 245,000 people currently, which is currently the largest widely available whole genome data set. With the diversity of our data set, we've observed variation in 1 billion locations already. And of those, quite a few, about 2/3 of those are not in NOMAD. Importantly, 113 million of those are in 3 or more of our participants and not in NOMAD. So, many of those have health record data, survey data, some have Fitbit data. Some of those are getting long read sequences. All those things to start to disentangle the actual clinical interpretation, the resources to figure out what those 113 million, basically new variation, what they might mean in our population clinically. We have linked to the American Community Survey as one of our, first data linkages that provides some environmental data. And this gets to how we currently have released location data. So right now in our privacy model, we have taken those home addresses and we have mapped them to a 3-digit zip code, and then used, in this case, the 3-digit zip code to a weighted average for those geographies for the ACS data, which comes from the census. And these are the data sets that we put in there. But other researchers can come in and use the zip3 data and link to other things. And whatever that resource, you can bring those other data sets in and use that. We have been working with other institutes and centers around different funding opportunities. We actually just had a meeting yesterday for our first set of administrative supplements, which are just basically ended at this point, are in the process of ending, that were specifically around using the resource. And we have a community of researchers essentially, and now we're adding to that with R03 and R21s, which we hope to announce soon, that we're a partnership with 27 other institutes and centers and offices in that process. So really a broad NIH support, including NIHS. And then active funding opportunities, you can see there. I encourage people to look at them. We have rolling applications now for people who want to engage participants or researchers or enroll them as well. And so it's an standing open other transaction award that's out there. And then partnerships with others out there that you can see. Researcher Workbench now has approaching 7,000 users, more than, basically that counts more than double this year. So we're really seeing a pickup in the number of researchers as time has gone on. That represents about 580 institutions. We have really intentionally sought to reach diverse institutions and researchers, just as we have with participants. And 74% of our researchers with our we have a metric of underrepresentation in the biomedical workforce, which includes stage, and also things like race and ethnicity, and what kind of institution they're at, whether they're at a minority serving institution, HBCU, MSI, HSI, in this process. And then our diversity metric by race and ethnicity includes anyone who's not Hispanic, white, or not Asian. And so we'd like to see that number continue to grow, and we intentionally engage in that process. These are some of the papers that have been published. There are more than 220 papers, I think, so far, and the most of those, I think over half of those are right around there, have been published in 2023. Probably not surprising. Things are increasing. Some of these are large studies, so you can see that meta-archive study of 2.5 million participants that have type 2 diabetes or controls, of which all of us are just a part. There are lots of studies. Health equity and health disparities are one of the most common themes of the publications that we see and the workspaces that are being investigated, which we're excited about. We, as cross-cutting across genomics, across epidemiological studies, and other kinds of elements. And then some specifics on the right, you see one where members of researchers from PrideNet looked at 12 common health conditions and some exposures in sexual and gender minority participants compared to those who were not sexual and gender minorities, and broke that out by different types of sexual and gender minorities as well, because we have that kinds of information in the resource. Here's a study that used the ZIP3 data. This study is in revision. It is available on Research Square right now, where they used ZIP3 data to map to PM2.5 data across the US. And you can see the mapping as it overlays with all of us participants that have electronic health record data. And then they used that electronic health record data and the ZIP3 mapped PM2.5 data to look at risk of various kinds of cancer. And so you can see those risk curves for different kinds of cancer modeled from all of us. And so environmental data is something that we want to expand, and we've been delighted to have NAEHS as really a great partner in this effort. We don't have much environmental data yet in the platform, and we really seek to change that. Last year, we held a workshop and summit with NAEHS and all of us, and those, you can look at that on the line and read about it. What came through. Some of you were at that and contributed to it. And we want to create a roadmap of how we really make this, fill in this pie piece that's missing right now. And this is some of how we've been talking right now in this process. One is having more broad data collections and linkage. We have this location information. And right now it's just shared at ZIP3, but we have the opportunity to do it at a more granular level. We are soon to announce a Center for Linked and Acquired Data, our CLAD award, which is a large award. We actually had a big meeting on this yesterday. And one of their tasks will be to link in environmental data using more granular location information. And we are working with NIHS in all of this, and really excited about the potentials for this. That will require some changes to some of our data access models, because we do want to protect participants' identity, and risk of re-identification is one of the major risks of the program. And so we'll probably have an application process for some of these kinds of data, and another tier of data that we will create in time. And that will, of course, have geospatial environmental data in this, and tools that we'll want to add into the workspace and make available to researchers such as yourselves. All these things we want to couple with training modules, of course. And then we're talking about an ancillary study specifically that will look at health, and looking at a subset that we can use our biospecimens combined with data linkages to go deeper on diseases, and such as type 2 diabetes. And so we are in active discussion with NIHS and other institutes, centers, and offices for how we might be able to create and link in exposomic data, things like maybe methylation data, and phenotypes to create a resource. And like all resources, the goal is to create these and make them available to the broad researcher community. I mentioned the CLAD award, and this is coming very shortly. This just gives you a sense of what we're really trying to do with this award. It's really started with some of the ideas that we know that are data from electronic health records that someone signs up for, is going to be limited. We are a fragmented healthcare system, and while these data are powerful, if we can integrate data from other sources, it will fill in some of the gaps, and we'll be able to close in those gaps because we're truly a national program at this point, and so we don't have healthcare provider organizations sending us electronic health record data across the country. But it also really importantly includes the kind of data that we talked about, like environmental data. So these data will be pulled in, all the stuff on the right that we see here with CLAD, mortalities, claims, residential history, getting more history data we might put in here, geocoded data that we can link in, environmental data, health information networks, and exchanges, and to pull these kinds of data in over time. Nutrition for Precision Health, I mentioned as our first large ancillary study that launched, I think it was April of this year. And it includes data, of course, starting point of data from all of us, and then we'll add quite a bit of information, as you can see there in green, going deep with about 10,000 people. And then the subsets of those 10,000 will actually do controlled feeding trials, either at home or actually within a controlled environment, where we'll get to measure the effect of different studies, different diets in a randomized fashion on things like the microbiome. All these 10,000 participants are part of all of us. All these data will eventually be part of the researcher workbench as the data are collected and then harmonized, curated, and released. So with that, I am done and happy to take some questions. I'm going to stop sharing so I can see you all better, and look forward to as much time we have for questions.
Thank you very much, Josh. That was a great presentation. I see Karen Vasquez has her hand up.
Yeah, thank you. That was really impressive. That's just a tremendous wealth of information and resources that you have there. I guess my question is, sort of in retrospect, maybe looking back, you have this tremendous resource. It seems the limitation is your patient or the people, right, that you have, and you have a huge number. But you isolate certain things or you give them certain surveys. But is there some way to predict the future? So we already have things going on in the future now. So you're thinking about things like the epigenome or things like that you could look at. Is there some way to sort of, I know you plan these things in advance, but how do you so you do have limited resources in your sets. So how do you sort of prioritize things for the future that you may want to use some of these samples that are limited, for example, or providing them with additional surveys that could really provide information down the road? Just a thought question, really.
Yeah, no, great question, Karen. I mean, really, resources are limited all around, and one of those precious resources is our participants' time. So, everyone has an idea for a survey. But it's pretty expensive to go through the process and its participants' time to fill them out. So we basically have that cadence of about one a year. Sometimes it's a little bit more, but generally it's about one new thing that we do with them. And then when they enroll, there's a lot more. We're working on reassessments now, and we've really thought about, hey, what do we want to reassess in our participants as well? What are the highlights of all the other surveys that we've had out there? Not just what they repeating what was initial component. In terms of what we do with our biospecimen, we collect a lot more than just DNA. We feel like we have the funding and the mandate really from Congress to generate sequence data. And so that's in our remit, and most of the other data that we generate from our biospecimens, blood, cell-free DNA, serum plasma, urine, will be through ancillary studies. So it's really our partnerships across, starting with other NIH institutes and centers. We're looking at public-private partnerships in the future, and then eventually we're looking to make available these kinds of things to external researchers as well through an application process. That's going to be down the line. I don't really have a time frame for doing that because we want to start within the NIH family and then build up this as a resource. But that's why I work with NIHS. We're trying to get other ICs on with environment really as being one of our our real foci right now. But we're having other conversations as well, other imaging, stuff like that too.
Great, thank you. Yeah, thanks.
And Phil.
Phil was next, and then Trevor.
Josh, good to see you, and great that you're making so much progress. It really is amazingly impressive. Kudos to you and the whole team. I know it's early in the days of environmental data collection, but it seems, obviously given the emphasis you're putting on it, it seems like it's the beginning of what could be an incredibly powerful message with respect to how changing environments are changing health. And I don't know if there's been any indications using the All of Us data, perhaps it's just too early, but clearly sort of those longitudinal studies that relate to the environment would seem to be something that is, I'm assuming that NAEHS and other agencies, other institutes are actually actively funding or thinking about funding. But it seems like really to get the message across about how our environment is changing, seeing firsthand how it affects people's health. I mean, it doesn't get more poignant than that.
Bill, great to see you, and appreciate the kind words. And I completely agree. I think we do have these longitudinal data. We get longitudinal work histories and location histories that gives a capability of doing some of these kinds of longitudinal analyses. One thing I want to emphasize is we are a platform. As a platform, we need, hopefully this came through clearly, we need all of you and your colleagues and communities of researchers to come in and make the discoveries on our platform. We aren't centrally guiding it. And that being said, I think there's real opportunities for things like gene by environment studies, looking at it in time, and then having the mental health and sort of the history. I mean, there's some in our latest survey released this summer, mental health and well-being surveys. We get like adverse childhood experiences, things like abuse. I mean, it's really tough stuff that has deep effects over time. And people have talked about methylation changes that are from things like that too. I mean, there are epigenomic kind of changes that are through these kinds of things. So there's real opportunities to do this, and we're really looking forward to seeing what happens, what people discover.
I might just build on this very quickly, just to say, particularly with respect to educating the next generation of researcher to explore these problems. It's just an absolute explosion of students interested in acquiring quantitative skills, but at the same time to address societal problems. I mean, this new generation, is facing a very different world, and they see it, and they're ready to contribute to it. So anything the agencies can do to sort of foster, obviously I'm particularly thinking about what happens with, data science students. I mean, half of all of the incoming students to our university have some interest in doing data science. I mean, it's stunning. And because they see that as being a way to contribute to solving some of these problems. So programs that actually facilitate this kind of use of the data would be great.
That's wonderful, Phil. Agree.
I think Janie and then Trevor.
Sorry.
Hi, Janie Ingram from Northern Arizona University, and I just wanted to ask about the absence of the listing for American Indian Native, Alaska Natives. I was at a meeting on Friday where someone presented on all of us, and it sounds like there's some tribal consultations going on. So it wasn't clear to me, do you have that data and you're just looking to how to have approval to present it, or have you not collected it? And if you do have it, and where is it with the approval process?
Yeah, I really appreciate the question. We have deliberately, with our consultation process with tribal communities, not put it in the curated data repository that we release to researchers yet. We have a number of individuals who self-identify as Alaskan Native or American Indian that have joined the program. And we had a consultation process that concluded through an elongated conclusion during COVID. It started before COVID. And at that point, we had a path to releasing these data, but some of the communities in that process said, we're just overwhelmed with COVID, and we understand where things are. So that we have, I'm really excited that part of the reason I'm here now, we have really started this process in earnest again. And I just found that we were ready to do it before based on our old, consultation process, but it seemed like communities weren't. They wanted us to re-engage, and I completely get that, because it's sort of been a long time, and COVID's really much longer than the temporal time. And so we have a series of listening sessions that happened earlier this summer. We have an upcoming consultation, which, gosh, I actually never remember the date, but it's September 26th or 28th or something like that. But it's very obvious on our website. We've done Dear Tribal Leader letters. Obviously, we've emphasized it with like the NIH Tribal Advisory Committee. So, I'll be mentioning it today at the IHS stack, and really looking forward to what those next steps are. But that's just the first step. And one of the things I also want to talk about here is right now, like we said, a set of rules that we agreed to, and promise we made to tribal communities. That's a little bit different in what they see in the interface, that we do not recruit on tribal lands now, all those kinds of things, right? The promises we've made, because we really want to do trust. And I also want to talk about what would be next? How could we partner more with you? What would be those next steps that you might be interested in? And we understand that will be probably often a tribe by tribe conversation. And we could look differently in terms of, actually understanding tribal affiliation, maybe partnering and recruiting in tribal lands if they want to, maybe some different rules around access. I'm really open to those conversations. So.
Oh no, I think we lost Josh. I think that's his end. We've got the rest of the Zoom going, yeah.
Josh, if you can hear us, you're frozen. You might want to, well, I'm just looking at time. We just have 2 more minutes left before we go on to our next topic. It's probably best that we move on to the next topic. I'll just say that there are real opportunities for ancillary studies, and I'll talk about one of those tomorrow, which could be a model for other ICs and other entities involved in biomedical research to be working with the All of Us cohort to conduct the types of gene by environment studies that we really need. And also bringing, I think one of our challenges in the environmental health sciences community is to bring to Josh and his colleagues, the exposomic strategies. What's the data that we need to collect to integrate it into this phenomenal program? Now, Gary, just in the couple of minutes we have left, I know you're on the advisory committee for All of Us. Do you want to make a few words about what are the opportunities for environmental health sciences?
Yeah, I mean, it's been great to work with Josh and his team, and they're very enthusiastic. One place I think that we should really be looking at are some of the other biobanks. Like the UK Biobank is much more mature, and they've been able to go farther along. Is like if we could think about potentially like piloting some of these approaches in the biobanks that are just farther along. Like for example, UK Biobank has all the proteomic stuff done. They've done NMR metabolomics already, and they're now working on some additional parts of it. But it's because they're that much farther ahead, like kind of learning from what they've done, and they've done a lot of geospatial exposome type analysis now that I think you've seen that preprint that was out about that, and I think it kind of could help guide some of the things we're trying to do with All of Us. But the one thing, like we didn't talk that much about this, but the whole thing, it's a biobank. I mean, there's going to be millions and millions of samples. They collected a lot. There's not going to be like now that you only need like a few hundred microliters to run stuff, I mean, it's almost an endless possibilities of what we could do in the future. And so I think a lot of these ancillary studies will be very important. Like, for example, on the nutritional one, there's going to be untargeted metabolomics, and that's going to be a good idea of what you can see in those untargeted formats of like 10,000 or something. So I think there's a lot of exciting data coming along, and it's very promising.
So Josh is on the phone now, so we do have audio, so we can take, I think we had 4 questions queued up. It was Trevor, and then Maria, then Patricia, and then Daryl. So if we could fairly quickly take those, and then we'll move on to the next presentation.
Josh, this is very impressive. I had 2 high-end questions for you. One was partnerships with other biobanks. Is there a way to make that happen? Many health systems are establishing their own biobanks. It seems to be like a duplication of effort. I wonder if there's some mechanism by which those people can be brought together. The other one is in terms of exposure assessment. Maybe you could comment on your relationships with the EPA. They have many nice exposure assessment tools.
Thank you. Hopefully you can hear me okay.
We can.
Great. So in terms of partnerships, we are working with other groups, other biobanks across the world. One is through Helping Fund, and our Chief Medical and Science Officer, Jeff Ginsburg, formally created and led the international 100,000 person plus cohort consortium, which has consortiums across the world with DNA. We have worked really deeply with UK Biobank, and looking to, we have a paper that just came out where we looked at a couple models of joint analysis, and they are moving to adopt the same common data model across their data to facilitate some of those analyses for their phenotype data, just as we have identified and harmonized things like what version of Dragon we're using to call our genetic data on, to try to make the sequences and the phenotypes as similar as possible. And in terms of exposome data, we are really guided by our colleagues here at NAEHS in the process, and eager to use and reuse data that have been generated by the EPA and others, in this process. So it's not an area I know the depth that you all do, and I'm eager to take that advice and chart a direction forward.
Thanks, Josh. Maria?
Josh, thanks so much. Maria Savasta Kennedy here from UNC School of Law. This is amazing, and I'm ready to sign up as a participant. And I'm just wondering, what do you tell potential participants who were concerned about privacy? This is an enormous amount of really useful data. What do you tell participants in terms of who else has access to it? The government, insurance companies, et cetera?
Great questions. We are really broad with the process, and I'm so excited you want to sign up, and you can firsthand experience it all. I encourage all of you, of course. In the process, we try to be really clear with our video and document-based consent process, including forms of questions at the end to make sure that participants got the key information, that the data will be broadly accessible to researchers. And then we have some videos that people can, other things they can read if they want to go deeper as well. We promise that we will do everything we can to remove all personally identifiable information, but we also did not promise that it's impossible that someone couldn't re-identify them. We have lots of protections around, and we're actually doing data loss prevention tools. We can look at suspicious activity that happens within the cloud, and we flag that, and we'll lock someone's account with automated approaches if we see suspicious activity. And we're always re-engineering and growing and thinking about what we can do. But ultimately, at the end of the day, there's also some degree of trust, and systems can have risk, and so we try to make sure that that is clear in the process as well. And we think transparency, trying to communicate, and just being upfront has been the way to approach that. And then on our other side, doing everything we can to protect privacy, because it really is job one. If we don't maintain that trust, we won't engender all the other things we want with the community longitudinality, the data donation that participants give, and so it is really critical that we have that.
Patricia.
Morning, Josh. I just had a question. For those tribes that have moratorium on genetic studies, how will you ensure, I guess, that individuals that are participating are not from those tribes? Because I know whether you recruit often on the reservation, many of these tribes, you know, their IRB process goes beyond tribal lands, their own tribal lands.
Yeah, Patricia, thanks for the question. Right now it operates as not recruiting off tribal lands, and it's all self-identification. And so it's part of the process that we've done, and this is one of the kinds of conversations we have. We don't have any idea if any of these people are actually tribal members. And as we actually go forward with deeper tribal membership and partnerships, it would be up to whatever the tribe wants to do. One of the things, for instance, that an important addition to the question I think Janie asked earlier is, one of the places we got to, and a real place of comfort with our tribal communities through consultation was, even though we're not releasing these data yet to researchers, we are letting them have their genetic results back if they want them. And so, we talked about that, we looked at that, and we said, an understanding and agreement that that those data, as these participants that we really don't know other affiliation, and people were comfortable with the rigor we've tried to put around making sure that we're not directly engaging and reaching out to tribal communities, would be comfortable getting their data back. So we are, in this point, if a member of our program wants that information back, regardless of what their self-affiliation might be, of any affiliation they may choose, they can get their own health data back if they want it.
And the last question from Daryl.
Thank you very much. I was just, I guess, and this is going towards the next session, Jay, just wondering about the overall input with respect to machine learning and chat GPT. So if you look at, right? Okay, and so all of us versus, your biobank there versus something like Gary just mentioned in terms of the UK biobanks, what are your estimations as it relates to overall equity in terms of the input to machine learning chat GPT going forward from EHRs, for an example?
Well, ChatGPT doesn't have access to our system.
AI, yeah. Well, let's say
but
we're
people
next
are
year.
using. Yeah. No, I just want. But I think it's important to clarify if anyone's
Yes,
curious.
sorry about that.
You do have to go through our approval process.
Yes, sir.
But people are using AI algorithms, and I'll give you one example of one that I thought was actually. I think it may have been the very first paper published out of our system by external researcher. They had developed an AI algorithm to determine who would end up needing surgery for glaucoma, and they developed a single site, and it worked really well at that site. And when they applied it at within the All of Us data, which had at that time more than 50 EHR systems contributing data, 14 different EHR vendor data, of course a wide range of geography and a diverse population, the algorithm was like a flip of a coin. It did not work at all. And this is exactly what you see with AI. You take an AI algorithm, if you don't feed it diverse information, then it can learn a local minima, so to speak, and get trapped in something that is not predictive. And so an algorithm that team retrained in our data, worked really actually quite well across diverse data. And it just shows the power of that. So, UK Biobank is an incredibly tremendous resource. And I'm sorry, I was lost in cyberspace when Gary was talking. So I missed his. Sorry. I would have loved to hear them. But, UK Biobank is a tremendous resource. They'll train lots of things. It is not a diverse resource. And so, we need both of these resources, and we need new resources to come on board that are, continue to recruit other diverse populations across the world. We work together. But I think that, yes, that would be a real potential problem if you just train something on the UK Biobank.
I think we need to move on. So Josh, thank you very much. This is very intriguing to hear your presentation and hear the questions. Although I want to clarify, I think you promised that the All of Us bus, the recruitment bus, is going to actually drive down and be here sometime in central North Carolina. Is that correct?
Rick, we will figure that out. We'll get it down there.
Okay. We're waiting for you. Okay, thanks again.
Great.
Okay, take care.
Thank you so much.
Goodbye.
So, and thank you, Daryl, for setting up our conversation for the rest of the day. So now that we've talked about one massive source of data, let's do a deep dive into what can we do when we have massive sources of data available, and where is the power of AI, machine learning, and other advanced analytics to make sense of very large and very complex data sets. So we've set up a series of presentations and a council discussion on this. And our first presentation is from Thomas Hartung, who is the director of the Center for Alternatives to Animal Testing at Johns Hopkins University. He's a global pioneer in the development and application of organotypic cultures and other advanced analytics for toxicology or for toxicity testing. And he's actually joining us from Europe today. He's at the Eurotox meeting, but thanks for joining us a little bit later in your day. And Thomas, I think you can share your screen and give us your presentation.
Sure. Thank you very much. It's a pleasure to speak from Slovenia once in a while. I have the privilege not only to have a few academic affiliations, but I'm also the field chief editor of Frontiers in Artificial Intelligence. And we have published in only 4 years 800 articles, which are in all areas of AI use. I'm also leading the section for medicine, public health myself. There's a lot happening. I was asked to talk about AI, NAM, and toxicology. AI, and everybody knows, NAM is in biomedicine often spelled as non-animal methods. In toxicology, it is typically spelled as new approach methods. And this shows you that toxicology still considers in vitro and in silico something new, and has not really been embracing it to the extent it might be doing. I've made my slides available. I have a QR code again on the last slide, but also a few papers in between.
And Thomas, sorry to interrupt, but we are not getting your slides as full screen. If you want to share them as full screen.
Not?
Nope.
Oops, that's strange. I have. That's strange. Okay. Then I have to stop share and let me do the following. I share my desktop and now go to the PowerPoint.
Okay, that's good. Yep.
Good. Okay. AI publications are steadily increasing. You see, 2 years ago already 2.5% of all publications. But I put this up especially to show you one thing which did blow me away. This is showing what the extent of publications is which are coming out of China. If the publications in Chinese are added, it is about 80% of publications which are coming from this single country. And you can see further, it is also the number of citations which is continuously increasing to this literature, and the number of patents. And I put this on because there's an ongoing discussion about possibly regulating AI approaches. And I think it is very important to understand that the music is playing not only in the transatlantic divide, where the models which are at the moment mainly discussed are originating. I had the privilege to develop or contribute to the transformative map for AI in human healthcare. This is also demonstrating that all areas of healthcare at the moment are being influenced by this new technology, which is possibly disruptive for this. And we are going to carry out a Keystone Symposium in December, where we are going to discuss the various applications of AI in healthcare, because there is not one of the 150 disciplines of medicine which is not affected by this type of technologies. Coming to toxicology. As a toxicologist, I have a long wish list of things. Unfortunately, the animal models, which are at the moment still the gold standard, which are used for essentially all of these, are not really doing a very good job on this. Mice and rats predict each other by about 60% for complex endpoints. Some of these tests are around $1 million for one endpoint, can take 5 years. We cannot really run them on the large majority of chemicals. There's 350,000 chemicals which have been registered in the 19 most developed countries, and we have good assessments perhaps for something like 5 to 10,000. We cannot use them for the biologicals, which are increasingly the drug entities which are being developed because they're human specific, and so on and so on. So I would simply say there's a lot of room for improvement, and AI promises to be exactly this. We should be clear that AI shines only if there is big data. So it is not about a big Excel sheet or something. AI is making big sense of big data. It is about volume, but it's also very importantly about variety, so that we have really very different pieces of information which complement each other. And it's about the velocity that they are accumulating, the 3 V's of big data. What we have seen is that there is an enormous synergy of data generation, computing power, and AI models. The data in the world are increasing by 60 to 70% per year at the moment, which means that more than 90% of all data in the world have been produced in the last 3 years. Computers are increasing in power, doubling every 2 years at half the price. That's Moore's law, which did hold 50, 60 years now. So it's a 40% increase in computational power per year. But AI, over the last 12 years, has doubled in capacity every 3 months, on 8-fold increase from year to year. And this has resulted altogether in more than a billion-fold increase in the power of artificial intelligence over the last 60 years. And this is what we are witnessing at the moment. And I feel reminded of this song by R.E.M., "It's the end of the world as we know it, and I feel fine," which I think is very important. And I want to show you why I feel fine with this. The turning point was really the introduction of deep learning. And there's one specific characteristic of deep learning, which is it is not having a ceiling. With more data, we're not making only smaller and smaller incremental steps. Deep learning is actually increasing its power, predictive power, with more data. And in toxicology and in all of science, we have increasingly a number of resources here. This starts with the scientific literature. The scientific literature is PubMed alone, 1 million articles per year, and 80% of them describe some chemical effects, not necessarily as drugs or toxicants, but very often as inhibitors, as chemical actors, stimulators, or whatever. We have increasingly databases, legacy databases of studies of the past, and animal tests alone. There's about $5 billion spent every year on animal testing in toxicology. We then have the internet data, the gray literature. We found 900,000 safety data sheets in the internet, which is, again, perhaps not the most reliable resource, but it is a piece of information about substance we otherwise have no information on. High content imaging, any type of image analysis. Thinking, for example, of digital pathology, the omics technologies, robotized testing like the ToxCast and Tox21 programs of the world, and sensor technologies in animals, in humans, from Fitbit to whatever, name it. And these are transforming really our field from a data poor to a data rich endeavor. And I like to call this toxicology because these different sources can now be fed into this increasingly available ecosystem of AI and machine learning systems. The large language models is one part, mainly around the different media which can now be processed, not even only language, but also pictures. But there's other technologies which are at the moment increasingly impacting. For us toxicologists, some of them are actually quite interesting, with blockchain allowing to exchange data without the possibility to breach, or federated learning, which allows to have an algorithm trained behind the firewalls of a company, let's say, and optimize the algorithms without ever transferring any data and sharing data with the public. Probably a model lawyers will accept, and we can get access to a lot of the data which are behind firewalls. The natural language processing part is at the moment getting a lot of attention. With ChatGPT, which was already mentioned, but there is Bard, there is Llama, there is Claude, and others, more and more of these models. Still, somehow P-Day in March was, with the release of GPT-4, was a very important point for many. Everybody has noticed that this is technology which is now in our hands. Last fall, 400 million people signed up for GPT 3.5 in only 2 months. This was the fastest rollout of a technology we have ever seen. And quite interestingly, if you see the corpus on which these models are being trained, Bard or GPT, about 9% of this is science and health information, which is already quite sizable. And what I found most remarkable is if you see what the most important sites are, and you see on top the open access publisher, which makes perfect sense. Without giving access to this information, the system cannot learn from it. And I think that this is really a very important point to tackle, the availability of scientific information to get good scientific use of AI. What is also quite remarkable is how quickly now human skills are being learned. Don't know whether you can see, but the first of these curves is handwriting recognition. It took about 25 years in order to get human quality handwriting recognition. But now we're getting faster and faster in these skills. This is a math test, an SAT test. It is code generation. While last year about 40% of all coding was already done by AI, it is now around 80%. So it is not a wise decision to become a coder anymore. To give you an example, GPT-4 performed at the 90th percentile on a simulated bar exam, and whatever you think of lawyers, that's already quite a bit of an achievement. And a year earlier, they were at about 10th percentile. And you see similar for SAT tests, very, very good values. The number of scientific publications is dramatically increasing throughout. And it is now really about making sense of a lot of this information and having this at the fingertip. And this is again the growth of these large language models with respect to the numbers of variables that were trained on. It's a logarithmic scale. And already with the bidirectional transformers, the very important step in AI with Google's development in 2017, there is fine-tuning for scientific literature. There were fine-tuned and pre-trained systems in order to better read the respective information and write in the context of science. With BioGPT, Windows released in February of this year a tool to pre-train the GPT AIs. And what this graph shows, BioGPT is already outperforming humans in annotating scientific papers. So it is reading them at least with the same accuracy as, let's say, one of my PhD students, but they're not reading one paper per week. They're reading millions in a day, and they don't forget. So this is an enormous opportunity here. This comes from a venture capital company, and they show here that already now, according to their assessment, these type of system write a good draft of a scientific paper, and they expect that by 2030 latest, they will outperform a professional scientific writer in drafting scientific papers. So we might be the last generation who really learned to write a scientific paper from scratch. And this was an opinion article earlier this year suggesting that we should use these open generative AI models and embrace them in science. And I think there is no other way. We cannot really block the use of these. To give you an example of personal experience, this was an article by a colleague in the Policy Forum of Frontiers, and I was asked to write a response to this, which I did. It was about arguing about regulation of AI. But in order to do this article, I asked ChatGPT, summarize the paper, praise it, and criticize it. And I added this as a supplement to my own article. And both me and the author of the original article both found this was a very robust response which we received, very solid. Certainly nothing really inspiring, because it was essentially summarizing these things, but it forced me, myself, in my own article, also to contrast to GPT, to look into more inspirational things, quotes, mindling in personal experiences, opinions, and the type of food for thought. And I think this is where we really, as humans, should focus the things which are not easily accessible. AI has been doing a lot of wonderful things, which we would thought of as miracles until most recently. I want to focus only on one, which I found really was for me a personal epiphany. And this is the first one, playing chess. You might have heard about DeepMind and their AlphaZero program, which never was trained on a human game of chess. They told it only in the morning to play. After 4 hours of playing and all failing and failing and failing, it was as good as Magnus Carlsen, the current world champion. And after 8 hours, it was at 3,600 elo points and unbeatable for humans. I put this up only for one point. The interesting thing is it plays chess differently. It is, for example, sacrificing figures much more than humans would do. And human chess players are now studying how AlphaZero is playing chess in order to improve their playing. So we should not only expect from AI that it is performing the tasks which are too much work for us or could be done faster. It is also about finding completely new solutions. So in the context of toxicology, it is really about data retrieval. There have been studies showing how often we are doing our risk assessments on incomplete evaluations of the literature. It is about evidence integration. If you think that, for example, there is about 12,000 scientific publications on bisphenol A, there is more than 5,000 publications on glyphosate. If these things should be integrated, some help of these type of systems is certainly very welcome. But it's also increasingly allowing us to predict toxic properties, to carry out or support pathology as a very important discipline for toxicology. And it is helping us with reporting, simply. Digital pathology, I think everybody has an idea about the role of image analysis, of high content imaging, of cloud storage, of standardized interpretation of these pictures. There is a lot of new science which has come about. AI comes in many flavors. AI comes not only in what we now see as generative AI of speech and vision and language. It is also important as an expert system, which is guiding us in possible decision taking, is helping with planning and optimization of processes, robotics, and it is capable of predictive analytics, making making an actual prediction. And I would like to refer to our own work in 2018, also already 5 years ago, where a relatively early form of machine learning was used on what was at the time a large data set, 10 million structures, 900,000 of them had some type of test data. And we could show in this paper published in ToxSci, and I say Tom Lichtefeld, at the time my PhD student, was the lead author of this, and we could show that applying a read across, which means looking into neighboring chemistry of similar structure, this very large database predicted actually 9 OECD test guidelines better than their reproducibility. For 190,000 cases where we had a chemical and its classification for certain toxic properties, hazards, we were 87% accurate, while the reproducibility of these tests was only on average 81%. So this was already extremely promising and mainly accomplished by the fact that we had network effects of the massive amount of information and transfer learning, which means compared to traditional QSAR, quantitative structure-activity relationships, we were not just staying within one property to be predicted, but if we were looking for eye irritation, let's say, we were also very much building on the fact that we knew something about skin irritation or skin corrosion, which makes immediate sense that this is informative also for eye irritation as an endpoint. And in this sense, we used 74 different properties of these chemicals in order to predict. This is giving enormous potential for replacement of animal studies. These 9 tests use 57% of all animals in toxicology in Europe. We don't have US data because we don't collect them for mice and rats. But imagine 57% of all of the animal tests to be replaced with something which seems to be not only faster and cheaper, but also probably even better. In the meantime, we have expanded this and challenging it with human data. For skin sensitization, we do have human test data for 506 chemicals, and the AI system predicted them 80% correctly, where the local lymph node assay as the preferred animal test detects only 74%. We also showed in another paper that you can batch process things. We took a list of 4,700 food relevant chemicals and let them run through the system, and in much less than an hour, it put out the equivalent of 38,000 animal studies, which would have cost more than $250 million to produce. And again, in a small validation set, we found 83% correct results, quite consistent with the previous work. And so far only presented as a poster at SOT in a Society of Toxicology meeting this year, we showed that this can also be expanded to cancer or reproductive toxicity. These are registrations with the European Chemical Program REACH. 950 chemicals had cancer data, 1,100 had reproductive toxicity data, and we were 75 and 82% correct. Again, clearly outperforming the reproducibility of some of these studies. There's a dark side to AI. We should be clear. We are also in the infancy of many of these methods. They are very data hungry, but there's a big problem. The answer has to be in the data. You always get a result, but we need to make clear that there is causality. We need to validate our results. We have to identify biases in the data sets. And interestingly, all of this can increasingly be done by the machine itself. There's the old saying of garbage in, garbage out, but the question is only who is identifying the garbage. Are we doing this as humans and reduce our data sets to something which is no longer big data? Or are we teaching the machine how to identify the garbage and work with this? But the way forward clearly is to have humans in the loop, to control AI at the moment is at best a co-pilot to this type of work. And we have to increase our emphasis on explainable AI, where AI names the reasons for proposing a certain result. Something which is at the moment only done on the cost of accuracy, but it is something which is increasingly possible. The possibility of data integration through AI is enormous for all of the areas of toxicology, from adverse effects, off-target effects, biomarkers, interspecies differences, and adverse pathways. I think that this is really part of the next wave of revolutionary changes which are possible in toxicology. We wrote this article discussing the 2007 report on toxicity testing for the 21st century, which has so much impacted our field, but this is now 14 years later. And our knowledge in the life science is at least doubling every 7 years, then we would have 4 times more knowledge. Some people say it is doubling now every 2 to 3 years, so we would have been 16 times more knowledge since. So it might be time for another version 2.0 of toxicology, or Tox 21. And this was an opportunity we were actually given by the Department of Defense. I found 2 co-chairs with Ana Navas Asien from Columbia and Baishe Shu from Texas AM. And with 30 forward-looking toxicologists, some of them on your panel, some 15 agency observers. And we came out in June with this report, which in the end is a call for a human exposome project. Understanding exposome, however, as a complement to the genome, not just as an exposomics project, but really something which is cataloging the health effects of exposure. There's an article where I'm commenting on this for those interested. But the 3 main messages were we have to make toxicology more exposure-driven. We have to enable it by new technologies like AI. And we have to integrate evidences. And points 2 and 3 are clearly benefiting from AI technologies. And I would argue that also the exposomic studies need something like exposome intelligence. I would like to quickly get your attention for an EU project which is running at the moment, which is applying the type of AI we are doing to liver, kidney, and developing brain. I have the privilege to head the AI part of this project, which is just in the middle of its 5-year term. And it is based on integrating, finding information from various sources. Tom Lüchtefeld, whom I already mentioned, has created, beside his PhD, 2 companies, and one of them has produced one is ToxTrack and has produced the program SysRev, which was meant originally to support systematic reviews by extracting, by semi-automated learning, annotate papers and find, after training on 100 or 200 papers, those which should be included for a systematic review. This is available free of charge in a public version, and more than 10,000 systematic reviews projects have been carried out on SysRev already. And within OnTox, we are expanding this to the extraction of information, the recognition of entities and causal relationships which we are receiving here. But besides ToxTrack and its SysRev program, we also make use of databases, and I will come to this in a second, the publicly available databases, and a meta crawler, ChemChart, which is reading all of the information which we can find on the internet on a given chemical. And this is the data sources which we are principally using in this project. Let's talk for a second about BioBricks. This was funded actually by the NAEHS, by the National Science Foundation, and by the EU. Tom and team have in the meantime developed 50 BioBricks. A BioBrick is a handle which is put on a public database of interest in public health, which means it is programmed so that you do not need to worry about the programming language, about the structure of the database, but it is importing this within minutes into your own computer system. And one example of this is ChemHarmony. ChemHarmony has combined only 8 of these databases, and this has given us already 200 million times where we had a chemical, a property, and a result. 200 million. Yeah? So this is an enormous increase from the 900,000 cases we had in our previous work, and together with some new similarity metrics, which are also including biological similarity, we are about to have tremendous things. We have seen, for example, that we could predict 125 different properties with always more than 80% accuracy. And this can increasingly be done with normal computers, while in 2018 we had to use a computer from Amazon for $5,000 a day. This can now be done on an essentially normal computer. It's a $20,000 computer, but still a reasonably available computer system. I really would like to emphasize that the strength of AI is the integration of evidence, the retrieval and integration of information. And we are trying to do this to feed our read-across-based structure-activity relationships on the one hand, but also to feed them into biology. So we are automatically feeding information into physiological maps, adverse outcome pathways, and other ways of visualization of biology, so that we ultimately see how much is physiology perturbed by a given substance, or what information can be gained from chemical structure and properties. And the goal is to combine this to a probability of hazard. Probability of hazard is really trying to move away from the black and white we typically use in toxicology, classifying something as toxic or non-toxic, to what science really can deliver, which is shades of gray with some uncertainty. And this has an enormous impact on the role of these tests, what is definitive, and makes new test results not a game shift, but a game changer. Not a game changer, but a game shifter here. We have really tried to revive the concept of probabilistic risk assessment by now integrating AI with its opportunities. And this is a white paper, which was part of this process. We've carried out 2 workshops in 2022 and 2023 to tailor this more to this idea of using AI for a probability of risk ultimately. So within the OnTox project, our big sense is developing at the moment a tool which wants to be a co-pilot. It does not want to replace the current methodologies, but says, we want to provide you with a probability of risk in an automated way, and demonstrating what data were retrieved to suggest this, and to start to enable an information economy, where we can ask ourselves, is it worthwhile to run this test, this animal test or other? Would it really change the information base? And would then move us to some targeted testing, for example, with microphysiological system, other to clarify those cases where we cannot decide on the basis of data. And this is the last point I would like to quickly make. We have seen another disruptive technology in parallel, which is the growth of microphysiological systems. And this is a science paper we were able to write on the basis of one of our workshops. As a shameless plug, we have just carried out the first 2 World Summits on microphysiological systems, and the third one will be next year in Seattle. But I wanted to bring this in because these technologies talk to each other. And in one of our major projects at the moment, we are combining brain organoids, one form of microphysiological systems, with AI, and give it feedback in order to explore to which extent these systems can communicate, can learn and memorize information. And we call this organoid intelligence. It is really to build systems for the physiology of learning, to study brain-machine interfaces. And in our field of toxicology and drug development, you can imagine some simple cognitive functions would be so valuable to develop models for Alzheimer or autism, which are functional endpoints and not just counting dead cells. But the engineers are also dreaming of biological computing as the future of this. We published this concept in February, which was enormously successful. More than 600 press hits followed. We have also published a workshop report for forming a community. The White House has taken this up as one of the bold biotechnology goals in March. The National Science Foundation has announced that they will follow the proposal I entered. Engineering Organ Intelligence will soon be a program there. And we are working at the moment to develop DORI, a dementia OI research initiative, in order to exploit this further. So I hope I have shown you that there is some revolutionary change taking place at the moment. It is really about integrating scientific knowledge, making it available to accelerate drug development. We have seen that last year already 18 AI-developed drugs entered human phase 1 trials, and this year the first of them did enter in a phase 2 trial. And I think this is optimizing public health and prevention, and it is also democratizing healthcare access. And I think that we all can contribute by open access, fair data, machine-readable information, helping to identify biases and create explainable AI. With this, I hope I have given you a panoramic of what is happening at the moment with respect to AI.
Thank you very much, Thomas. We do have some time for some discussion. Trevor.
Tom, this is Trevor Penning from the University of Pennsylvania. Great presentation as always. I wanted to ask you about two things. In your algorithm for doing read-across analysis, the endpoints have different predictability. For example, if you think about genotoxicity, it's going to be dealing with reactivity. If you think about repeat dose, it's more metabolism-based. So I'm sure your algorithms take this into account. Is that correct?
Yeah, in the end, the algorithm is finding what is most informative for a given thing. So mutagenicity, for example, with reactive chemistry, is very informative for anything which is corrosive, or also very informative for sensitization, because you need haptic information as an important step. We have not tackled repeat dose toxicity. This is, for me, the holy grail where we have to move to. And the problem is mainly the data. There's not enough standardized data that you can actually use for a repeat dose. We are at the moment manually curating repeat dose data from all of the REACH registrations because we want to analyze this. Cancer and reproductive tox, we were very surprised about the high predictivity of these. So obviously the genotox data in the mix were already quite helpful here.
So in terms of the repeat dose and metabolism, do your algorithms use metabolic simulators?
We have added metabolic simulators to understand whether some of the activity cliffs and outliers are explainable by this, and we were not impressed. But we only did this for skin sensitization and trying to predict the human data. It was a marginal increase by also considering possible metabolites, and you get a lot of mess because they are predicting so many possible metabolites. It is very difficult to really get something which is quite precisely predicting what the metabolites is you should encounter. It's not an end to the discussion, but as I said, our first impressions were a bit disappointing.
It's very impressive. So my other question is, you were talking about hazard versus non-hazard as an all or none or a binary situation. Do your algorithms take into account exposure assessment or toxic threshold of concern?
The read-across based structure-activity relationship, not at all. They deliver a probability of falling in of classification. That's what they're at the moment delivering. The OnTox project, however, has an exposure arm, and there we are using these two. We're trying to bring in the XFOCAST type of high throughput exposure assessments, and we're bringing in thresholds of toxicological concern. But I have to say that this is the weaker arm of the ONCTOX project. We have only very few groups who are dealing with this, so I don't think that we will come to some definitive answers. But we are hoping also by expanding, for example, in our close collaboration with NAEHS and the NAEHS, to get more and more external help in building such a large model. Yeah.
My final question, if I'm permitted, would be for the research scientists in academia, how easy is it to access some of the tools that you've developed?
Our goal at the moment is to make this a full open access tool, which comes out of ONTOX. The original tool was developed with support by Underwriters Laboratories, UL, which you will know as a safety standard organization, but it was behind a paywall. Yeah. And but we have seen that the uptake of the scientific community is minimal if there is not encouragement on the regulatory side on the one hand. So we are at the moment trying to develop all as open access within the ONTOX project. Yeah.
Thank you so much, Tom.
Phil.
Yeah, that was really inspiring, I have to say. I have sort of overarching meta question, I guess. One, well, as it relates to two sets of stakeholders. One is the funding agencies themselves. I mean, this is all moving so incredibly fast. What should funding agencies be doing that they're not doing to facilitate this kind of work? I suspect so much funding is still going to things that, frankly, are a little, well, I should say, behind the curve. So that's the first stakeholder. The second, which of particular interest to me, is in academia, the training that we're doing for the next generation of people to actually make these contributions, in your case in toxicology, but from my point of view more generally. Are you starting to see the sense that you're getting students that have the basics in training to actually sort of take all of this to the next level in a way that's really socially and probably acceptable?
Yeah. I mean, first of all, I think the enormous public uptake of AI at the moment will give us a wave of pre-trained and highly motivated students who want to apply AI in all parts of life. And I also think that AI in principle is the answer to information flooding, which we are all seeing. It is really giving us the opportunity to condense a lot of information, find our way in all of the things which are available. If I only take toxicology, the keyword of toxicology, there's per year 20,000 articles in PubMed, published with toxicology as a keyword. Nobody can read this all. But AI is helping us to condense this and get the information. And I think we simply have to embrace it. At the same time, we must not have autonomous AI. We need the human in the loop. You have responsibility for the content you generate because these systems are hallucinating. These systems often answer questions where the data are not available. And this is really important that the responsibility stays with us. But it is enormously increasing productivity, getting you information sources you would otherwise never have seen, or also identifying that something has already been done, that there is information outside and does not need to be repeated in the next grant, because very quickly this can be identified. And what the agencies can do, from my point of view, is first of all force even more open access publishing, machine readable publishing, and the fair data accessibility. Because if you get taxpayers' money, then the society should benefit from this, and this is only achieved by giving them access to the results.
Couldn't agree more. Thank you.
Just a quick question. We don't have a lot of time left, but how do you envision these powerful tools that you've described over the last hour or so how could they be used to help us better understand how individuals respond differently to different environmental exposures? So it's the whole gene by environment effect, integrating, complex genetics and genomics. The genetics responsible for differential exposure are complex. It's not a single gene. It's potentially hundreds of different gene variants. And then integrating epigenetics into this. So are you factoring that into your exposomics strategies and your thinking about using AI in toxicology science?
Again, a golden grail, a holy grail for toxicology to understand inter-individual differences. First of all, we need data. AI is no solution if there's no data. At the moment, for data generation, I really see these microphysiological systems, these stem cell-based systems as ideal, because here you have a patient with a disease and you have the respective genetic background. And by either introducing risk genes or by repairing risk genes, you can see what the consequence is. Doing this, my own group has shown, for example, the first pair of a risk gene and a risk chemical, CHAD8 and chlorpyrifos, to synergize strongly in some hallmarks of autism generation. And this was the basis for creating now an Autism Excellence Center, which is following 175,000 mother-child pairs in order to identify such gene-environment interactions, for which we then, in our brain model, are trying to find mechanistic evidence that there is actually such a link. But this is the long way. My hope is that, however, from more of these data and higher throughput type of methodologies, we're already much, much faster than any animal model would be, but we are still slow. But faster types of these models, and then combined with the exposomics type of approaches we have so nicely seen, which are at the moment benefiting from large-scale biobanking and exposomic studies, these together gives the information for AI to interpret and put some hypothesis forward, which we can follow up in our experimental systems.
So just another quick question here. So I think we all can appreciate the value of the NAMS approaches, using those in vitro 3D microphysiological systems. But our understanding is that a lot of the biological impacts on individuals are going to be epigenetically driven, as a consequence of environmental exposures. So how well do those in vitro 3D microphysiological systems recapitulate some of the epigenetic modifications that may be occurring within the individual?
Yeah, unfortunately, most is wiped out. So when you're reprogramming these epithelial cells of humans, you're losing most of the epigenetics. However, some diseases are representing themselves. For example, if you take cells from an Alzheimer patient, the induced pluripotent stem cell-derived neurons will show some of the pathophysiology and histopathophysiology of Alzheimer. But this is enough to see a functional impairment. That's exactly what we want to do with OI. But we probably will have to work harder on how we can reproduce also type of epigenetic pre-treatment of our systems, that we create the memory on which we then later see what the second hit is doing, or how it is changed.
Great, thank you.
I think in the interest of time, we better move on. So I'm going to turn the microphone over to my colleague, Dr. Mary Wolf, to introduce our speaker from DTT.
Good morning. I'm pleased to introduce Kamal Mansour, who is a computational chemist in our Division of Translational Toxicology's Predictive Toxicology Branch and the NTP Interagency Center for the Evaluation of Alternative Toxicological Methods. Kamal is working on several projects that involve QSAR modeling, chemoinformatics, and computational toxicology, working to help use computer tools to understand chemicals and their effects on health and the environment and make it easier for everyone, including non-programming experts, to use these tools. And so he and his research team have developed a modeling and visualization pipeline called MOVIS, and now he's going to tell you a little bit about it. Thank you. Kamal.
Thanks a lot, Mary, and thanks to everyone here. Thank you, Council, for giving me this opportunity to present our MOVIS pipeline. So it's about democratizing cheminformatics, and this is just one of the applications of AI and machine learning tools in DTT, in particular in our branch, the predictive toxicology branch. So the idea is actually, I'm really grateful for the first two presentations, and especially the nice overview by Thomas Hartung about all these tools and how we can use them. And that actually makes my job a lot easier giving this presentation. So just like it was already mentioned in the previous presentations, AI is everywhere, and we're going to use it in so many different ways. So this is just one of the ways that we're envisioning one of its applications for our branch. So in my presentation, I'll speak a little bit about the concept of democratizing cheminformatics, and then I'll talk a little bit about the MOVIS platform. I'm not going to show a movie. And then the platform that we used for building this pipeline, and then giving one example application, because this presentation is really about the applications, since we already have an overview of these tools from the previous presentations. So the way I want to start talking about this, and the idea, the whole concept is this. So a lot of you remember when in the early 90s, at least myself, when I started playing with computers, like even text processing used to be like you needed to know certain commands to be able to like see the beginning or the end of the text, or like grab specific parts of the text, and it really required some expertise to even do text processing. Fast forward with Microsoft Windows and a lot of the graphical user interfaces that are made available. Now everyone is using these tools. You write your own text, you write your own emails, you do your own PowerPoint presentations, which many years ago used to be like only reserved to very highly skilled experts to do that. So in my opinion, the idea is that in the next few years, everyone will be able to do complicated machine learning applications, apply cheminformatics workflows to their own needs without having to require an expert in programming or knowing these machine learning algorithms like from the inside. So these are the cheminformatics needs that a lot of groups are now using, but in a way that only experts are only applying them. So for example, like all what is related to, okay, so all what's related to data storage and access, like loading and storing data, data mining and curation, data processing from different sources, and then also data analysis and visualization, and then also applying machine learning and AI tools to build models and making predictions, and then again related to the data storage, store those data sets again in the databases and make them available for others. So all these are the needs for cheminformatics that are available right now only for experts. The idea of the democratization process started really with making code available in publications. So a lot of publications now, they make their code, they share their code that they use to train their models, and also to make their predictions and to analyze the data and all that. So that's really great, and that's really the first step. However, that's not really enough, because again, the code is available on GitHub, or it's not well documented, and only experts really know how to use it. And then an expert needs to be proficient in that specific language that was used to write that specific code. So again, sharing is great, but it's not enough. We need user-friendly interfaces, and we need step-by-step guides and documentation so that these tools are available and used by everyone and democratized. Like I mentioned, the code is available in so many different languages. And as mentioned earlier by Thomas Harting, that maybe it doesn't pay off anymore to be a coder, because you will be only expert in one specific language, but the code is available in so many different languages, and all these tools and all these publications that come out every day are written in specific languages, or certain pieces of them are written in specific languages. So are you going to be an expert in all of them to be able to combine things together into your workflow or to do what you want? Or are you going to rewrite everything in one specific language, and that will take you a lot of time? So the idea is the no-code to low-code development. And this is how we think the democratization process is going to happen. And we think that in the few next years, everyone will be able to use these tools that are available from papers, not only the new papers, but also the old papers that provide pieces of code that do specific tasks that you just want to grab and plug and play in your workflow without having to rewrite it in a specific language, or without even having to know that specific language that was used to write that code. And for that, this is one of the platform that a few know about for now, but I'm sure a lot of you will be hearing more and more about it. So it's called NAEHS, and it's a platform. It's free and open source, and it provides a lot of amazing tools that cover different data science needs, like data access that I was mentioning earlier, data visualization, data preparation, and also applies machine learning and AI tools, and text mining, data mining, all those data needs, data preparation and curation needs. But what's really important here, and the reason why we chose it, is that it allows to combine pieces of codes from different languages. And it also allows the use of not only proprietary software, but also open source and free software. So you can have a platform that does it all. And you can combine all these pieces together, just like you see in the animation, piece by piece, these small things called nodes, and each one of the nodes is performing a specific task. So you build your own workflow, really, and then grab existing code and put it in one of the nodes. One of them will be in R, the other in Python, the other in Java. And the future of programming is actually the feature language, if you want to call it that way, of programming. It's not Java, it's not R, it's not Python, it's no coding or no language at all. Because just like when we made that transition from command line text processing to the user interface, well, in the background of that user interface, there are still commands being sent to the operating system. It's just that you don't know about them. And you don't care, really, because you don't really need to know what's the command to make a text bold, for example, or underline it. You don't really need to know that. Same thing here. That piece of code is performing a specific task, and you combine them together, and you connect them by these pipes that carry data and commands in different languages, and you don't even need to see what's going on. If you want to see it, there is also an expert face to it, and you can modify that as well. You can also build your own nodes, but you don't really have to as a beginner. And after you build your workflow, you can share it with your colleagues. You can work on it together with other colleagues or programmers in other parts of the world. You can make it available not only on GitHub, but also on NAEHS Hub, which is a space where these workflows are shared and these components are shared. So the idea is really as in the small diagram here, read, transform, analyze, and deploy. And deployment is the next step that we're carrying this whole process further, because you can always build your own workflow, make it available as is, meaning as nodes like this. And any user can, who wants to build their own workflow, or they want to modify it a little bit, they can still execute it in this form. But we're going a step further, and we're deploying it to NAEHS server, which is a way of that takes that specific workflow in this format and makes it as a web application that is completely intuitive and very user friendly. And this will be facing the user, and the users don't even see the original workflow if they don't want to. They only see the interactive face that is processing their data and building their models and making all those predictions. And for that, we're applying we're deploying it to the NAEHS server that we have a license for right now. But the pipeline, the platform itself is free and open source. And this is really the movies pipeline. So we took all those previous needs about cheminformatics that I mentioned earlier, and we built different workflows to process data storage and access, and do data mining and curation, data visualization, and a little bit of modeling as well. And those workflows work together, are connected together, combined in a way to form this movies pipeline that provides access to all these tools and needs without having to write your own code. So like I mentioned, we have a license for the web portal, which takes the original workflows and makes it in a more user-friendly web application way. And it's available. All these workflows are now available on this platform. And for now, it's behind the firewall of NAEHS or NIH in general. So anyone with a NIH login can have access to it. Later on, after we make publications, we will make it available to the public. But for now, it's behind the firewall. And this is also an important note based on what was mentioned earlier in the couple previous presentation, when related to security and also privacy. So you can build your own model using one of these workflows, make it available to your colleagues behind the firewall, and it's not gonna be public if it's trained on certain data that are not public. So it remains within a specific circle where that data can be used without any breach of data. But the workflow, the empty workflow itself, can be shared because it will process other data. So there are like two types of workflows: the workflow containing the data itself and after execution, and the empty workflow that anyone can use and apply to their own applications. And one of the applications of these workflows is chemical groupings. And we know how important it is. It was also mentioned earlier related to read across and grouping chemicals. And it really helps us understand how chemicals work, how certain characteristics of certain chemicals affect in a certain way or cause certain toxicity or biological activity. And this is really to help everyone understand the basic concept grouping chemicals, and it's really similarity, because similarity is very relative, and it really depends on what's your goal behind grouping those chemicals. You cannot group chemicals in only one way and say this is the only way to group these chemicals, because what matters to you is what determines how you group your chemicals. Just like these shapes here, you want to group them by shape, colors, size, or pattern. And each one of them might be relevant for a specific application, but you cannot always take it only the shape, because just they look alike, you know. And same thing for chemistry. You have this example of 16 aldehydes. You can group them by common scaffold, like the chemicals that really look alike, or you can group them by functional groups. And both groupings might be useful for a specific application. It's just you need to know the goal of your grouping. And this is just an example to show you the importance of those functional groups, so that we don't always group chemicals based on the way they look. Just because they look together, we need to study them together. Just because they are called PFAS, we always take all PFAS chemicals together and we study them together. Certain PFAS look like other chemicals that are not PFAS. So maybe they share certain common features that might be helpful in studying PFAS based on some functional groups that makes them active or inactive for a specific assay. So it's really like this imaginary dragon from the Ishtar Gate. So it has different components, right? Like horse, wrapped up, snake, you know. And same thing for the chemical. It has, someone has their mic. Can you please mute yourselves if you're not talking? So you have this chemical and you have all these characteristics of that specific chemical. And it really depends on the goal of your study to make use of the classification or to select the properties that are the most relevant for your for the endpoint that you are studying. We actually did organize here at NAEHS a clustering and classification workshop where we studied all these approaches, and the presentations and the expert insights are already still available on that website of the workshop, and we're also publishing a paper about it soon. And we took all what we learned from that workshop from those experts and applied it to this workflow of grouping chemicals, which takes all the previous step that I mentioned of curation, data curation, and data analysis, and it applies certain machine learning algorithms and AI to do either an unsupervised clustering, which means you just want to study the chemicals. You don't have a specific endpoint to study. You just want to explore your data, your database. Or you want to do a supervised grouping based on machine learning algorithms, because you have a specific endpoint to study. And you want to select even the properties of the chemicals that you want to study based on that specific endpoint that you're trying to either predict or model or group your chemicals based on it. And we, within this workflow, we're also actually providing visualization of the results, and I'll show you a quick demo later, but we're also applying the power of GPT to help users interpret the results. So that, because there are a lot of parameters and a lot of different algorithms, so we implemented GPT in a way that we send comments that combine the different pieces of information, and then it generates an interpretation of a specific figure based on that data, so that the users who are not very proficient using a specific algorithm or knowing about a specific property of a chemical, that they have a better understanding. And of course, the output of the workflow is provided in different formats, and we also provide the configuration file that to rerun the analysis using another data set, or even to visualize again the same study, so that your study or your project is not lost once you're logged out. So this is how the workflow looks in the platform called NAEHS. So each piece of the workflow processes or does specific tasks, and it might look complicated, but once you start using it, it really is less complicated than seeing 7,000 lines of code. And this is really how it looks like. So you click on one of those specific squares, and each one of them perform a specific task. For example, these nodes here, when you go to the web portal of the workflow, this is what you're going to see. So you can upload your data, you can select what you want to do, and then you also have a guide on the side to tell you what's going on here. And when you're seeing this, you're not even seeing this. You don't even care what's going on in the background. But if you are an expert and you want to modify it a little bit, you can go back here, modify a little something here, and then it will appear on the web application. So this is a short demo of how it works. So you start with that initial page that where you have a description of what you can do at the start, and then you can load your data set using a file that can be in different formats: CSV, Excel, PDF, SDF if it's about chemicals. And you can select whether your data is labeled or unlabeled, meaning that is it you're going to be studying a specific endpoint, or are you going to be studying just the chemicals themselves independently. It will ask you like which column contains your data and which column, and it will know by itself the column that contains the chemical structures. And then it will help you select the molecular descriptors, which is what I mentioned earlier about the chemical having multiple properties, and the algorithm will have to select specific properties that go the best way for that specific endpoint, so that at the end, when you do your clustering, the clusters are meaningful for that specific endpoint, meaning that you don't do the same clustering, or you don't end up with the same number of clusters no matter what's the endpoint. It's very, very relative. And machine learning algorithms will help you select the best descriptors for your endpoint. And it will guide you through all the different steps of selecting the parameters of the algorithm, so that you have the best results depending on your goal. And on the side, you always have the guide that tells you what to select and how to select it, or you can always leave it to the automatic way, because like you see in this page here, you can do it in a manual or automatic way. So if you're an expert, you can do the manual and you can do things yourself. Otherwise, you can select the automatic way, and then it will know what's going on and how to prioritize the descriptors, or how to select the best parameters for that specific algorithm. And also for the algorithms, you can select specific algorithms depending on what you're planning to do, and you have the guide on the side that tells you a little bit about each one of the algorithms, so that you know which one to select, and for the visualization as well. And it's the, I would say the most advantage to this type of interface is that it guides you step by step, so that you don't skip important steps. And that's what we see a lot of times, because there are a lot of software that provide ways to do analysis and visualization and clustering. However, you will need to know where to click and where to start and which steps, so that you don't skip very important steps. But in this platform, all the steps are guided, so you cannot skip very, very important steps, and you end up with the optimal results. And at the end, it shows you the results, it shows you the figures, and it also helps you interpret the results. So for example, at the end, you have the interactive visualization where you can select certain chemicals of one specific cluster. You can look at them, you can see what do they have in common, and also it will help you understand which functions or which properties of that specific cluster that brought them together to be grouped in that specific cluster. Also, at the end of the at the end of the analysis, you can download all the results, like I mentioned earlier, into different formats. And this is going a bit slower than, okay. Yeah, so. Okay. The joys of the demos always. Anyways, it's okay. So I still have the results and interpretation as a separate slide. So for the results and interpretation, like I mentioned earlier, you have the different clusters. You can study them one by one, and you can understand, like for example, for this specific cluster, what are the properties of the chemicals that contributed to those specific structures being grouped together into that specific cluster. And you see the most important parameters. And this is really the GPT interpretation that we have included here that tells the user of what's going on, why those chemicals were grouped together, what are these features that made them most important for that specific cluster, and how it relates to the endpoint that is being studied. So this workflow is already being applied to solve specific problems within DTT, and also in collaboration with other teams. And we're taking a couple databases and we're doing clustering and then selecting certain chemicals for prioritizing testing of chemicals. So these are two of the collaborations that we're applying this workflow for. So the first one is about the MRI Global selection of 100 compounds out of 4,000 for some experimental testing, and also the NeuroSeta, which is selecting about 100 compounds to screening through the Rosetta array technology. And with that, I would like to thank you all. I acknowledge our team. It's really the work of our brilliant postdoc, Jose Teofili Moreira Filo, and also our other NAEHS collaborators, and also all the PTB colleagues and the PTB director, David Drive, who provided a lot of useful feedback building this workflow and the whole pipeline, as well as improving it. And we hope it will be relevant to a lot of you, and I encourage everyone to go take a look at the pipeline and apply it, play with it, and let us know if we can help in any way. And I'll be happy to take any comment or question.
Thank you very much, Kamo. Questions? Daryl?
Yeah, very good. I like that. I don't understand why I wasn't aware of this before today. But anyway, now with respect to dimension reduction, are you able to input what you want in there, or do you have to go with those pre-selected categories? For an example, if I want to look at paracletes, so look at some pleat-centric technique,
yeah,
can I input that in?
Yes,
okay.
you can input that, and that's thanks for the question. So the dimensionality reduction, I did not focus on it there because for the sake of time, but it's a very important step because a lot of times we input all the descriptors the way they are, and then a lot of descriptors end up being irrelevant or zero variance at all, no benefit to the final results, or very highly correlated, and that will skew the results as well. So that the step of dimensionality reduction is very important, and it provides specific techniques to do it, but you can also do it manually. Like it gives you all the flexibility to do that by yourself, either following what's available like automatically, or if you're an expert, you can do it yourself as well. Yeah.
Great. I'll email.
Yeah. Thank you.
Trevor.
Very nice. I have a couple of thoughts for you. So I'd like you to comment on how your cluster analysis differs from more traditional decision trees based on chemical structure. And the other comment I had for you is, early on in your presentation, you talked about PFAS-related chemicals. I'm not sure if you've seen it, but there's a paper in Chemical Research in Toxicology which actually identified 14,300 different PFAS chemicals and arranged them into 140 chemotypes, which is based on a more traditional decision tree approach.
Yeah, so the decision tree is actually one of the algorithms that we provide in the pipeline itself. So you can select decision tree, you can select k-means clustering, you can select any of those very well-known algorithms. The advantage of using this over using the what you call the classical decision tree is that you have to be very knowledgeable about that algorithm to be able to have good results, have good classification, because there are a lot of other hidden steps like the dimensionality reduction, right? So a non-expert would probably skip some of those very important steps. So this application, this workflow really guides the user through all the different steps and will not skip any important step, depending on what's the algorithm that's being chosen. So yeah, decision tree provides really good clustering, but you need to know how to apply it. And that's the difference here. And about PFAS, yeah, I agree with you. There are a lot of different, chemicals, and you can, like I mentioned earlier, it's really the goal or the what are you trying to do with those PFAS? What specific property are you studying? For example, even if you're taking one specific endpoint, you can either study PFAS as only PFAS that are known as PFAS, or you can also mix them with other chemicals that are not PFAS, but might share some properties. And that way, you can, for example, read across based on the property. At the end, when you have in the same cluster some PFAS and some others that are not PFAS, and it shows you in a convincible way that, oh, they share these exact same properties, and that's why they are together in this specific cluster, and you see that they can share those same functional groups or those same properties, and it makes sense that those properties are what causing that specific endpoint, and these other non-PFAS were tested, but this one is not. You can maybe relate, you can maybe do some read across, and that's really the usefulness of the step of interpretation at the end, because grouping chemicals together is possible. You can do it so many ways. It's really the interpretation that makes a study convincible and scientifically sound or not, in my opinion.
Thank you.
Any other questions for Kamal? If not, thank you again. Thanks to our other speakers this morning. We're now going to take an hour-long break for lunch, so we'll return promptly at 12:30 for our next speaker.